and he's going to talk about the Amplitude Bootstrap.
Let's see. How's that? Okay, great. So thanks very much to the organizers of this conference and also for the organizers of the Aspects of Amplitudes workshop that preceded that. It was great to have a chance to spend 3 weeks in Stockholm, which I was last at 34 years ago. Good to be back. So I wanted to tell you about a sort of program for determining amplitudes in planar n=4 super-Yang mills with as little detailed information as possible. So although this represents one of the millions of Feynman diagrams that you would need to do the 6 gluon amplitude at 5 loops, that's the last Feynman diagram you're going to see in this talk. In fact, you aren't even going to see any integrands. We're only going to look at sort of the final results for integrals after making a conjecture for what form they have. We're going to impose sort of external data without looking inside the loops. And this is a program I've been working on for a few years, and the most recent, and you probably heard, many of you have heard some versions of this talk before. I apologize for the parts that repeat. I'll try to wake you up for the new parts, okay? So the point is there are some things that we missed the first time around that really supercharge this program and make it work a lot better than in the initial incarnations. And the most recent work is with Simone Caron-Moix, Matt von Hippel, and Andrew McLeod, and we're finishing it up now, but I'll tell you about what we know right now. Now, many people here know that n=4 super-Yang mills has some pretty amazing properties. Of course, we all know that it's conformally invariant. The beta function vanishes for any value of the coupling, so it's sort of a marginal line of conformal field theories. Another very interesting property that holds in generic n=4 super-Yang mills for any gauge group, doesn't have to be large n SUN, or at least we think it holds, is that the amplitudes have a certain uniform transcendental weight. Very roughly speaking, they look like 2L iterated integrals, or even more roughly, log to the 2L of x at L loops. Whereas in QCD, you tend to get functions like that, but then things of lower transcendentality, all the way down to rational terms in the L loop amplitudes. When we go into the large NC limit of SUN gauge group, we find even more amazing things happening, which many people here have contributed to the development of, so don't need to go into a whole lot of detail. One of the things, though, that isn't focused on quite as often is the fact that the perturbation theory suddenly becomes better behaved. So most quantum field theories have an asymptotic perturbation series that has factorial growth in it for one of a couple of reasons. One can be renormalons, terms that go like the beta function coefficients to the n times n factorial. Since we have a conformally invariant theory, those terms are absent. Also, even in conformal theories like n=4 super-Yang mills at finite NC, we have instanton contributions, and those also tend to lead to a zero radius of convergence of the perturbative series. But at large n, we don't have those, and the perturbation theory has a finite radius of convergence. And we're going to later on see sort of numerical indications of how that can be seen in these high loop order scattering amplitudes. Also, it's emerged over the past 10 years or so that the amplitudes for 4 or 5 gluons are trivial to all loop orders. We understand their kinematic dependence completely. This is intimately related, as many know, to dual conformal invariance and even a dual superconformal invariance that's associated with the n-gluon amplitudes. And that in turn is related to the equivalency between amplitudes in this theory and Wilson loops. It also gives us a strong coupling handle where the Wilson loops at strong coupling can be evaluated in terms of minimal area surfaces. And then finally, we have, at finite coupling, we have some amazing results from integrability and the operator product expansion. It gives us exact predictions in the near collinear limit, as Benjamin outlined on the first day of this conference. Of course, integrability is a key to solving exact problems exactly without perturbation theory. Of course, integrability has been around for a long time in various guises, and in classical physics, it's critical to generating non-chaotic, non-precessing ellipses in the case of things governed by inverse square laws, such as orbital mechanics. And there's a conservation of an additional quantity in addition to the energy and the angular momentum. There's this Laplace-Runge length vector, which is conserved. And at the quantum level, Pauli used it to solve for the spectrum of the hydrogen atom and finding the additional O4 symmetry that's only broken by relativistic effects. And in a version of planar n=4 super-Yang nulls with masses, Simone Caron-Hua and Johannes Henn showed that this Laplace-Runge lens vector is within the class of dual conformal transformations. So given this extra symmetry and its historic role in the hydrogen atom, you can really say that planar n=4 super-Yang nulls theory is a hydrogen atom of the 21st century. And we should use it as a testing ground for many ideas in developing quantum field theory. And in fact, what seems within sight is solving planar n=4 super-Yang nulls. In some sense, this has already been done at finite coupling for operator anomalous dimensions and nearby quantities. And Benjamin reviewed some of that in his talk. And the question is, can we extend these ideas and try to solve for the scattering amplitudes in this theory for arbitrary kinematical configurations? If we can do that, then we can really play around with the kinematics as well as the coupling and try to get a more concrete picture of holography at finite coupling. Because as you probably all know, when you go out to strong coupling, the theory of planar n=4 is dual to the strings propagating in ADS5 cross S5. And we can then try to see exactly how gluons in one picture in perturbation theory morph into strings as a function of the kinematics and the couplings. So many people here have contributed to the development of the idea that amplitudes in this theory are essentially the same as Wilson loops. The amplitudes live in a space-time with the momentum of the external gluons, and the dual space-time, the amplitudes correspond to these light-like polygons with vertices at the dual coordinates x1 to xn. And then, of course, there's also a momentum twistor space that is very convenient for parameterizing these things. When we go out to strong coupling, these Wilson polygons, the way you want to compute them, as pointed out by Alday and Malacena, in that strong coupling limit, there's the dual picture in terms of ADS5 cross S5 is very useful, and the string world sheet spans a minimal surface in this theory, in the ADS5. And this, the signal model that sort of governs this behavior has a classical integrability, as pointed out by Bena, Roybal, and Polchinski, and that leads to a method based on classical integrability called the thermodynamic bubble ansatz, and also a Y system to effectively solve this minimal area problem numerically for generic kinematics. At finite coupling, I won't say much about this in detail because Benjamin reviewed it very well 2 days ago, but there's a picture where everything is built up out of atoms, and the atoms are the pentagons, which correspond to essentially butyl-Wilson n-gons, these with various pentagons, and some over flux tube excitations that propagate between them. And in this case, you can build up the operator product expansion governing near collinear limits of the amplitudes at finite values of the coupling. And then if you want, you can expand those out perturbatively in order to compare with high-order perturbative results. And then we have weak coupling, where we could use Feynman diagrams, but I promised you I wouldn't show you any more of them, so I'm going to stick to that. And it would be extremely cumbersome to try to do this via Feynman diagrams. Now, using the duality to the Wilson loop, the first sort of non-trivial example, the two-loop hexagonal Wilson loop, was computed by Del Duca, Dürr, and Smirnov. And as you probably all know, that was simplified to a very compact formula in terms of classical polylogs by Goncharov, Spradlin, Volovich, and Burgu, using the symbol of an iterated integral. So we have an ability to do things at weak coupling as well, which is actually going to be the focus of the rest of the talk. But before I get into those details, this is sort of the big picture I want you to take away. And the idea is that we have good control at strong coupling in terms of minimal surfaces, or sort of arbitrary values of the kinematics, which are just sketched here as a one-dimensional plot. So we sort of understand things everywhere here, although we don't have a great understanding of how to perturb around strong coupling for generic kinematics. Over here, near certain limits, like the collinear limit, where things are dominated by these low-lying flux tube excitations, we also have good control. That control extends uniformly from weak coupling to strong coupling. And then, in perturbation theory, the bulk of this talk is going to be about making progress at high orders for generic kinematics. And then we have a lot of overlap here with the flux tube picture, but the ultimate goal is to reach the holy grail here and try to get a picture of the scattering at finite coupling and also for generic kinematics. Of course, we're not there yet, but that's a great goal to have. So in this Hexagon function Bootstrap that we've been working on for a few years, the idea is to use the analytic properties of perturbative amplitudes in this theory to determine them directly as much as we can without ever peeking inside the loops. So we don't need to use to look at specific integrands, even if we might know what they are in some form from the amplitudehedron. We want to look at the generic class of functions that have the right shape to be the solution to the problem, and then determine them on general grounds. I mean, the motivation for doing this is because we want to eventually do this at finite coupling, where we don't have individual loops to look at. We should try to do everything as well as we can without looking toward inside the loops. So the general program is actually very simple. Once you make an ansatz for infrared finite versions of the 6-gluon scattering amplitudes as linear combinations of things we'll call hexagon functions. And now we understand that they live in a much smaller space than we thought a year ago. So that's something I want to describe. This much smaller space comes from things called the Steinmann constraints, which I'll explain in a little bit. But they dramatically reduce the size of the ansatz by a factor of almost 10 at 4 loops, and even more at higher loops. Once we have constructed an ansatz that obeys these general conditions and some certain global conditions we know, then we want to use some boundary value data, or how the answer behaves in various limits, in order to fix remaining constants. And we'll see that we need amazingly little, let's call it sophisticated information to do this, once we fall into a subspace that satisfies the Steinmann constraints. All of these operations are basically linear algebra. The ansatz is a linear combination of known functions with unknown coefficients that are going to end up being rational numbers. So at the end of the day, the thing that limits this is just solving linear equations with rational coefficients. And so far we can do it on laptops through 5 loops. We'll see what we can do after that. And at the end of the day, once you have a unique solution, since you made an ansatz or a guess, you should cross-check it. But there's a huge amount of data in these boundary values that we don't need to use, that we can use as independent cross-checks. So what I want to show you today is that this works fantastically well for the 6-gluon amplitude, which is the first non-trivial amplitude in planar n=4 super Yang-Mills. And because it turns out that both the MHV and NMHV amplitudes are basically coming out of the same function space, you can do them both in parallel. And you heard also that very similar ideas apply equally well to the 7-point case from Mark Spradlin's talk earlier in the conference. So So what kind of boundary data can we use to either fix the ansatz or cross-check it? Well, I already mentioned we have the OPE limit that applies when 2 of the 6 gluons become parallel. And when you expand around that limit in the kinematic variable that's vanishing, the power law terms in the expansion are different numbers of flux tube excitations, basically. There's also a multi-regi limit, which was also described earlier in this program by Benjamin and also by Claude Dour. And so I won't actually say that much about it, even though that's one of the boundary conditions we can use to fix some constants. And then there are a couple other limits, which I will say a little bit about later in the talk. You have multi-particle factorization, and there are certain self-crossing limits of Wilson loops that are quite interesting. But there's also one sort of global piece of information, which I'll come back to later. There's a dual superconformal equation called the descent equation, or the Q-bar equation, that was first studied in 2011, and it's very powerful as well. Global equations are much more powerful than boundary conditions, because they really fix things, you know, or constrain things everywhere in the phase space, not just on some corner or edge. So, a couple years ago, I got in the mail from Brown University this nice hat. Apparently it stands for Brown Dining Service. But I've discovered it's very effective. It protects me from infrared radiation as well as ultraviolet. So I'm going to stick with it for a little while. So the so-called BDS ansatz accounts for all the infrared divergences of the amplitude, and it also manages to account for an anomaly in dual conformal invariance due to these divergences. It fails for n equals 6 and 7, but it's been very useful nonetheless. The failure function, or the remainder function as we decided to call it, is dual conformally invariant, and that's been a focus of a lot of study, calculation, and analysis over the years. Anyway, this is what the BDS ansatz is. It's the tree amplitude times an exponential involving the powers of the Iterative coupling and certain constants, including the Cusp anomalous dimension as buried in here, times the full one-loop amplitude. So that depends on all the Mandelstam variables and also on the dim right parameter. And this was motivated by the infrared structure of QCD amplitudes and form factors. But basically, when you divide this out, you get a nice function left over that has dual conformal invariance. And most of you know what dual conformal invariance is, so I'm not going to belabor the point, but if we introduce in this box integral these 4 dual coordinates, then it is rewritten in this very compact form. And if you perform an inversion symmetry, which is sort of the non-trivial generator of this group, then you find that this box is invariant. We don't want to look inside the loops. We only want to apply dual conformal transformations to these external x's from now on. But if we do that, we find that the amplitude is a function of the external kinematic variables should be a function of these dual conformal cross ratios, which are made out of the separations between the dual vertices, which are in turn sums of cyclically adjacent momenta. So every amplitude we want to write down should be written in terms of these cross ratios once we've removed the dual conformal anomalies that are related to the infrared divergences. And because the adjacent ones are light-like separated, those don't give us invariance, and we can't actually make any of these cross ratios for 4 and 5 point. And so at the 6 point level, we get precisely 3 of these ratios, which we call U, V, and W. And they can be written either in terms of the dual conformal invariance or the ratios of Mandelstam variables. And you'll notice the 2-particle invariants appear in the numerator, and the 3-particle invariants appear in the denominator. There are branch cuts, for example, associated with branch cuts in the 2-particle or 3-particle invariants, which extend from U equals 0 or U equals infinity. We'll come back to that later. So the BDS ansatz can be used to define the remainder function. Since this had the full one-loop amplitude in it, the remainder function starts at 2 loops. And also there's nice properties of the remainder function that it vanishes in the collinear limit and so on. But I do have to take this hat off now because it turns out that there's a much better ansatz than the BDS ansatz, which it took us a while to figure out. It's called BDS-like. So I should have gotten a little post-it with like, but anyway. So the BDS-like ansatz at first sight looks just like the BDS ansatz. These constants here, which only depend on epsilon, not on the kinematics, they're exactly the same as in the BDS ansatz. And the first one at each loop order is called the Cusp anomalous dimension. But this quantity here is not the full one loop amplitude. Instead, it's been trimmed down. You take the one loop amplitude and you can add to it or subtract from it, if you think of this as minus something else. Subtract from it its complicated part. It has a part that has dilogarithms of the cross ratios in it. And if you remove that, because it's dual conformally invariant, the thing that's left over will still be dual conformally invariant. But the most important thing is that when you do that, what's left over here, that is the pole pieces, and certain pieces that sort of soak up the dual conformal anomaly, they only depend on the 2-particle invariance. They don't depend on the 3-particle invariance. Why that's important shouldn't be clear to you yet, but it will be in a little bit. So we're going to work, for the most part, with this BDS-like ansatz. And we'll see why it's a much better thing to do. If we divide the amplitude by the BDS-like ansatz instead of the BDS ansatz, then instead of that ratio being e to the R6, e to the R6 gets shifted by the difference between BDS-like and BDS exponentiated, and it turns out there's a factor of the Cusp anomalous dimension in there. So the relation between this normalized amplitude, which we want to work with now, this curly e, and the old remainder function is that it's e to the R6 minus gamma cusp over 8 times y, where y was this symmetric function of the totally symmetric function of u, v, and w that just involves these polylogs and logs. Okay, so the fact that there are no 3-particle invariants in this denominator of this expression will turn out to lead to simpler analytic behavior for curly e globally than the remainder function has. So since we have a 3-dimensional phase space, we can actually plot it here, and there are lots of interesting regions. There's a point at 111 where everything reduces to multiple zeta values, and I'll show you some of that later. There are also various lines where things reduce to simple harmonic polylogarithms, which I'll mention later as well. And then there's sort of limits where there's physical information near the boundaries. This line here is the near collinear limit. So when you expand functions around, the answers around these lines, they must match the operator product expansion that was evaluated by Benjamin Basso, Amit Sever, and Pedro Vieira. And in this limit, the multi-regi limit holds. This limit for the multi-regi limit is obtained after an analytic continuation where you dive into this wall and do a complex rotation by 2 pi I and then come back out here. There are also various spurious pole constraints and so on. And when you go off to infinity, that's the region where 3-particle invariants vanish. And their multi-particle factorization happens there, and the Steinmann conditions can be analyzed out there too. So of course this was covered by Benjamin, this limit, finite coupling, and so on. And we heard also about the multi-regi limit in his talk and Claude Doer's talk. And I'll mention this self-crossing limit a little bit later. So the basic bootstrap assumption is this ansatz that I've been alluding to. Still haven't quite told you what it is, but it's that the L-loop answer is a linear combination of weight 2L hexagon functions at any loop order. That's sort of a single number corresponding to the bosonic Wilson loop or the NMHV amplitude. In the case of the NMHV amplitude, it's a little more complicated structure in that there are R invariants that have been found at tree level, and the structure of them has been elucidated at loop level several years ago by Drummond, Hen, Korchemsky, and Sokachev. And so we can define a ratio function, but we're not going to use exactly a ratio function. We're going to, instead of dividing by the full MHV amplitude here, we're going to divide just by the BDS-like MHV amplitude. Again, so that we have only 2-particle invariance in the denominator, and we otherwise don't touch this numerator as much as we can. When we expand it, we find the same expansions as for the previously defined ratio function in terms of Grassmann containing superconformal invariance. And these coefficients here, called E and E tilde, they're also transcendental functions that are going to be drawn from the same space of weight 2L hexagon functions as we draw curly E. Any questions so far? All right. So many of you know all about generically what these kinds of functions are. There are multiple polylogs or iterated integrals, which can be defined by their integral representation, or if you have suitable boundary conditions to fix constants, you can define them by their derivatives. And so the derivative of such a transcendental function, basically anything that has a symbol, has the form of a sum over d logs of various rational functions of the underlying variables times these coefficient functions. So we call these the n-1, 1 coproducts. We don't really need that much about the full structure of the Hopf algebra. We just need to know that the derivatives can be expanded over a finite basis of transcendental functions of one lower weight. And then we can iterate this. So we call this is called the n-1, 1 coproduct, and it reminds you that this is a weight n-1 function. So then you can take the differential of this set of functions and define things that are n-2, 1, 1 coproducts, and so on down the line. And once you've iterated this n times, then you get to the symbol of the original function, which was described and exploited in the two-loop remainder function simplification by these folk. So a very simple example of this, which is also sort of a subspace of the hexagon function space, are the harmonic polylogarithms that were introduced first to the phenomenology community by Remedi and Vermazerin back in '99. So they're going to be a subsector of our space, and they generalize the classical polylogs, which are defined by integrating dt over t many times from an initial guy, which is a log of 1 minus t, or a dt of 1 minus t. But Remedi and Vermazerin realized that this was not really a complete space, and it should be generalized that you can integrate dt over t or dt over 1 minus t at each step. Or equivalently, you can define these things differentially up to constants by saying that dh of 0w, the 0 tells you you're integrating dt over t on a weight vector made out of zeros and ones. That allows you to append the 0. The integral dt over 1 minus t, you append a 1. Or differentially, things are always d log of u or d log of 1 minus u. So clearly the symbol alphabet for this case is just u and 1 minus u. In the hexagon case, without going through all the details, when you use the momentum twisters as described by Mark, for example, it transforms simply under the dual conformal transformations, but they're not projectively invariant. We can build 4 brackets and then find projectively invariant combinations. And it turns out that the letters, due to this relation, the A3 cluster algebra, are simple ratios of these 4 brackets. And so the original cross ratios have this kind of 2 over 2 ratio, and 1 minus the cross ratios of this form. And then there are 3 more, what we call parity odd letters, the Y's. And so this has been, the connection to the A3 cluster algebra has been understood in these papers, as well as similar things for n greater than 6 glue line amplitudes. Since there are only 3 kinematic variables, the y's are not independent of the y's. but they have a square root relation, so that there's a definition of the y's in terms of u, and z plus or minus, which have this square root of delta in it. And there's a parity operation, which flips the sign of the square root and inverts the y's. And so we can split the space into parity odd functions whose symbols have an odd number of y's, and parity even functions that have an even number of y's. And that grading sort of helps simplify the linear algebra that you have to do in constructing this function space. The first thing we do before we construct the function space is we sort of say, what's the first letters of the symbol? Or what are the functions whose derivatives eventually we have to wind up with when we compute all the way down. And Gaiotto, Maldacena, Severin, Vieira pointed out that the first symbol entry always has to be not any one of these 9 letters, but just a subset of the three cross ratios. And that's because the branch cuts in massless scattering amplitudes are in either 2-particle invariance or 3-particle invariance. And they always start at the origin in these variables. And since the cross ratios are simple ratios of these, those can have branch cuts starting from 0 or infinity. And at the level of the symbol, which is like the logarithm of u or 1 over u, they basically start at the origin in the symbol entry. However, 1 minus u, for example, does not, there are no branch cuts, or there is a sheet in which the amplitudes are completely smooth at u equals 1. And so you don't get 1 minus u as a first entry of the symbol, and you don't get the y letters as a first entry. And this is already a very powerful constraint. At weight 8, we counted up the number of multiple polylogs that we would have if we didn't have the symbol entry, and we found 1.6 million of them. And when we impose this entry, we find exactly 6,916. So for a while, we were pretty happy about that, but it turns out it's not the end of the story. This is still way too many. Many of these functions cannot possibly be involved in the amplitude. And okay, now you can wake up if you heard parts of this talk before, because this is the new stuff. I want to tell you about the Steinmann relations. And the Steinmann relations actually go back to a couple papers in German in 1960, and they have been studied over the years in sort of the school of the analytic S-matrix in the 70s, and also in the context of amplitudes and the multi-Reggie limit. They were studied by Bartels, Lepatov, and Savio Vera. And the basic message is that amplitudes should not have overlapping branch cuts or double discontinuities in 2 channels that are overlapping. So a cut divides the external states into 2 sets. And if the next cut further partitions that set, that's called an overlapping cut. The next cut could be over here and divide up one of the sets but not touch the other set. That's a non-overlapping cut. So here we're talking about overlapping cuts. And in fact, when you try to analyze cuts that overlap, where one of the cuts involves a 2-particle invariant, it can be confusing. The reason is that to change the sign of a 2-particle invariant in a massless theory, you have to move something from the initial state to the final state. And then the signs of other invariants flip around at the same time. So it's hard to keep track of how you're doing things independently. But in the case of 3-particle invariants, you can understand there's a very mild thing that you need to do to change the sign of the 3-particle invariant. So let's look at 3 goes to 3 scattering, where 1 plus 2 plus 3 go in and 4 plus 5 plus 6 go out. And let's first look at a region that would be involved in calculating the discontinuity in the channel S345. And in that case, we've set things up so that these 2 scatter. This one's massless, and this one can be almost on its mass shell and propagate a long ways over into this scattering. And at the multi-loop level, you can propagate pairs of particles as long as they're pretty collinear in the same direction. So that's sort of the region that's responsible for the S345 cut. But once you take that discontinuity that discontinuity function sort of remembers that you got to have real momenta propagating in this direction. And over here, you have a similar configuration, which is responsible for the cut in the 2, 3, 4 invariant. But they're incompatible restrictions. And once you've taken this discontinuity, you've imposed really a constraint on propagating particles here, which is inconsistent with them having real momentum propagating the other direction. So that's the generic argument that these guys here are propagating in sort of the wrong direction for this other discontinuity. And as a result, the discontinuity in this channel should then not have a discontinuity in this channel. And that's basically the Steinmann constraint for this specific case, but it generalizes any time you have overlapping cuts. If you have cuts that don't overlap, you can obviously have particles have intermediate states that scatter here, then rescatter over here. So just to give two examples, this is essentially the same example, I guess relabeled. Any 2, 3 particle cuts of the that are distinct in the 6-point case, their double discontinuities would violate the Steinmann conditions. In the 7-point case, you can have a double cut in, say, S123 and S567, which would not violate the Steinmann condition, but other ones do. So what does this constraint do? We're working with these dual conformal invariant variables, so we have to inspect them and see how they're made out of these 3 particle invariants. And the interesting thing is that the U has 2 different 3 particle invariants in the denominator. The logarithm of U has a branch cut from log of S123 in one channel, and log of S345 in another channel. But because it's the sum of the 2 terms, the double discontinuity vanishes. It's just a logarithm. But as soon as you square that logarithm, you get a cross term between log S123 and log S34, and that violates the Steinmann constraint. So log squared of U is not allowed as a sort of function in the 2, 1, 1, 1, 1 coproduct of any function. We'll call those Steinmann functions that obey that. Now there are some combinations of logarithms that we can square up, and that's UV over W, and it's cyclic images. If you look at the formulas for UV and W, you see that U over W cancels the S345 out of here, and V over W cancels the S234 out of here. So this thing is basically log of S123 up to some 2 particle invariance. And so you can raise this log to any power, and it's still a legal Steinmann function. The upshot is that before imposing this condition, when we looked at integrability, we find that there were 9 hexagon functions, but there are only 6 Steinmann hexagon functions. These Li2s of 1 minus 1 over U, if you look at it at infinity, you'll see that they go to constants and don't have any double discontinuities. And then these guys are okay. And then there's also this constant here, zeta of 2, which in principle we could add to this basis. So basically we've lost just 3 functions. But because everything piles up, that is, everything at higher weight is required to have derivatives that are consistent with this, it ends up being quite restrictive, as we'll come back to in a little bit. Oh, I should also say that there are very analogous constraints that Mark also already showed you some of the counting that you can do of how many functions are left after you impose these constraints at the 7-point level. And it's possible to do this because there's also a BDS-like ansatz in the 7-point case. So the basic idea is that you start with these weight 2 functions, and then you start to build higher weight functions. And the rule is that the derivative is completely of a generic hexagon function is characterized by that symbol alphabet and the sum over d logs. And you can write it out explicitly because the logarithm of yu, its derivative with respect to u, has this form, and similar things for yv and yw. So this is sort of the master formula. You can figure out what is the most general set of Steinmann hexagon functions at a given weight, if you know them at weight n-1, by inserting the general linear combinations for the weight n-1 functions that appear here. Then you just make sure that the mixed partial derivatives are equal, which is called an integrability constraint, but it's of course not the same as quantum integrability. And after applying this, you've fixed almost all the constants, but there's a few more conditions that fix coefficients in front of things that have simple zeta values in them that are required to maintain the space of good branch cuts and the Steinmann conditions. So there's like a handful of extra conditions that go into that. Then basically, you can just do some linear algebra and keep building up these functions at each weight. Now, the very first true hexagon function that has a parity odd letter in it is the d equals 6 scalar hexagon integral, which we call phi 6 tilde. It first appears at weight 3, and it's totally symmetric in u, v, and w. It could be written in terms of classical polylogs, but because those are few and far between in this story, we don't really pay much attention to that. What we do like to do is describe it, like everything else, in terms of its coproducts. If we take a coproduct of it, that is, look at its derivative and ask if it has a d log u in it, it doesn't. Why not? Because it's the first parity odd function, and this thing would have been a weight 2 parity odd function, but there aren't any of them, so it must be 0. And all these other coproducts with even letters must be 0 too. The only independent 2, 1 coproduct is when we take the yu, and that gives a function that is actually known as omega 1, which is a d equals 4 integral with some chiral numerators, and it explicitly looks like this. This coproduct relation actually is another way of encoding a first-order differential equation that was found a while ago for this integral. It's just a repackaging of it. So there are many more hexagon functions. Some of them are higher loop integrals, where you can find various integrals that appear in the representations of from the BCFW on-shell relations. But now I want to go back and tell you a little more about the combinations that we want to write down in order to describe these amplitudes. So we're going to enumerate these functions. I'll show you how many there are in a table in a second. And then when we impose some constraints, we can determine all these coefficients. A very simple constraint in the NMHV case is that this should be totally symmetric under permutations of u, v, and w, which is kind of a manifestation of a SUSY-word identity in the original NMHV amplitude. It should also be even under parity, and so we only have to look at parity even sector of functions. And it vanishes in the collinear limit. That is, R6 vanishes. E does not vanish in the collinear limit. You might think that's a bad thing, but we know exactly the relation between R6 and E, and it just involves simple polylogs whose collinear limit we understand very well. The one other global constraint I need to mention, and I'm not going to go through it in a whole lot of detail, comes from dual superconformal invariance. About 5 years ago, Simone and Songhe and David Matt Bolmore and David Skinner found a relation called either the descent equation or the Q-bar equation, in which there's a first derivative that operator representation of Q-bar on the amplitude. The general derivative has an anomaly with a source term from an n plus 1 point amplitude of one lower loop. You could use that to construct the amplitudes all by itself, but then you would need to understand very high point amplitudes as well. What we do instead is we sort of look in directions where the source term vanishes. And then we get homogeneous constraints where we don't need to know anything further about 7-point amplitudes. In the NMHV case, this final entry condition or constraint on the first derivative of E is very simple to state. Instead of there being 9 possible letters, there are only 6 of the 9. So U and 1 minus U don't appear independently, they only appear in this ratio. In terms of the coproducts, it's equivalent to the statement that EU plus E1 minus U is 0. These other two are related by the S3 symmetry. And there are some similar constraints which we can write down for the NMHV case. Thanks. So this, in some sense, is the grand table that tells us how well this program is working. So what we put in here is separately for MHV and NMHV, the number of parameters left in an ansatz for this E function, and I should have put both E and E tilde in here for the NMHV case. So there should also be a tilde on top of this as well. So in the left-hand column, it's MHV, and the right-hand is the total number of parameters for NMHV. And we were able to count the number of hexagon functions through weight 2, weight 4, weight 6, weight 8. But we don't even know how many hexagon functions there are according to our original definitions of hexagon functions at weight 10. We aren't able to solve that problem. However, it's now irrelevant because we know that these functions here really lie in a much smaller space. At weight 2, for one loop, it doesn't look that much smaller. It's only those 7 functions I showed you before. But you see, by the time you get to weight 4, it's half the size. And at this point, it's a quarter of the size, and here it's about an eighth of the size, or something like that, of this case. So it's probably about a 16th of the size in this case, but we don't even know how many functions there are here. Then we impose symmetry, that's S3 symmetry for MHV, and there's basically a Z2 symmetry for NMHV, and we get a little bit smaller space. Then we impose final entry conditions. I showed you the one for MHV, and there's some similar set of conditions for NMHV. At this point, we're down to, at worst, 272 at the 5-loop MHV number of parameters. And this final entry condition is somehow almost orthogonal to the collinear limit constraints. Once we put them in, we have at most 15 parameters left for 5-loop NMHV. And so all of this is sort of very elementary conditions. And then the next step is we choose to impose, we could do things in a different way, a different order, is to impose the multi-regi kinematics. So that's basically a factorization assumption. And then there are constraints on the BFKL eigenvalue and impact parameter that enter those formulas that were described by Benjamin and Claude. But we could self-consistently determine them at lower loop orders. And at each order, we need to go one higher order in the log expansion, but we would have determined that already if we didn't already know it from other sources by the previous loop order. So once we reach 0, 0, we're done, and the amplitude's uniquely determined. So we can do all of that, putting in very little extra information. So we don't need to use any of the OPE information anymore, like we used to use. Instead, it's a total cross-check. And there are some other conditions that we used to use as well. There were some next to final entry conditions that Simone had worked out. And in the NMHV case, we used to rely on a spurious pole condition. And very interestingly, after we impose Steinmann, these conditions don't do anything. They don't reduce the number of parameters at all. So we just chuck them out now. So now we've got these 4 or 5 loop results. We can analyze them in various limits, besides the ones that the few that we use to constrain them and learn interesting things. And one of the interesting things learned in the work with Ilya Esterlis was to do a close analysis of a self-crossing limit where has an interpretation at the amplitude level which looks a little like double parton scattering, where a gluon splits into 2 gluons, and then each of them, and on the other side, each of them rescatters in a 2 goes to 2 configuration. This is a physical realization of one of the Landau singularities that you could discover through a kind of analysis that Mark talked about earlier. And in the Wilson loop, it corresponds to folding the hexagon over so it almost intersects. And there's a specific way that you get into this kinematic region. It happens to overlap the multi-regi limit at one end, but it's an independent limit in its own right. It has some very interesting properties, like the singular terms are totally independent in this function of what value of V you're in. And you can derive some of these relations using Wilson loop renormalization group equations similar to those found by Korchemsky and Korchemskaya a long time ago. Another limit is NMHV multi-particle factorization, which was first studied by Byrne and Gordon Chalmers, and then at the one loop level, then we could extend it to the multi-loop level and find that a certain factorization function here has a very simple exponential form, and this corresponds to taking u and w to infinity. The simplicity is probably closely related to the Steinmann conditions. And anyway, we can rewrite in this limit in the NMHV amplitude, which is the only one that has a 3-particle pole at tree level, we can rewrite the answer and take a logarithm of the coefficient function there. And we find that this u has a very nice polynomial form where you get log squareds of one particular ratio, same one we have seen in the Steinmann relations that appears there. This polynomial has very nice, simple coefficients. And in some work, Amit and Benjamin and Pedro have studied this from the flux tube picture as well. So in the remaining few minutes, I just wanted to show you some numerical results. We're going to plot the perturbative coefficients on various lines and surfaces, and one of the things we're looking for is how close are we to asymptopia. What does asymptopia mean? Well, we think that if you get to large enough loop order, the ratio of successive loop orders, which we might call R6 bar for the remainder function, should go to a constant, -8 in the units I've been using. That's because the perturbative expansion in these units has a finite radius of convergence. And this radius is 1/8. You can study the Cusp anomalous dimension to see this. If you remember, Benjamin had these pictures of cuts in the rapidity plane, and when you take the coupling G, he called it, to be imaginary, those cuts start to move towards the real axis and they hit it at exactly this point. So there's a reason for this radius of convergence. Before I show you numerics, let me just show you a few analytic results. I said that everything becomes multiple zeta values at 1, 1, 1, and Mike Green defined for you the multiple zeta values, so I don't have to define them. I can just show you that at this point they pop up in our answers. Zeta 5,3 pops up at weight 8, and zeta 7,3 pops up at weight 10. Now let's look at some numbers. Here's the Cusp anomalous dimension, which is known to all orders, the work of Weiser, Eden, and Staudacher. And if you imagine things or you look out to 25 loops or so, you can see this is starting to go to -8, although it takes a long time to get there. And then this ratio function, the remainder function, the ratio of successive loop orders, it's in the general area of -8. But it doesn't actually keep going uniformly in the right direction. It has this kind of glitch here, which is related to the fact that the remainder function by definition is 0 at 2 loops, so this first ratio is infinite. It takes a while to recover from that. Amit suggested we plot a framed Wilson loop at some different points, and there things sort of go uniformly. And we can also look at a couple of lines and surfaces, so I'll show you some results on this line here, and then on this surface, and then we'll wrap up. On this line here, everything collapses to these harmonic polylogs of u. By the time you get to 5 loops, they're weight 10 harmonic polylogs, and here's the ratio of weight of 5 loops over 4 loops. And you can compare it to 4 loops over 3 loops and 3 loops over 2 loops. And when you do that, you sort of see that things are softening out, and if you have a good imagination, you can see that everything is going to -8. We haven't done the same plot at 5 loops yet, but at 4 loops you can see ratios of successive loop orders on surfaces are also quite flat until you get near the boundaries. At the boundaries there are logarithms and these ratios can't stay flat. And then there's a remarkable feature which we actually need to plot again, or I should replot at 5 loops, where if you divide things by 1, 1, 1, you see that even at strong coupling, this function looks very similar. to the weak coupling behavior. And there's some weird things happening in the odd part. Beyond 6 gluons, we heard from Mark Spradlin that cluster algebras provide very strong clues to the right functions, and they've made some amazing progress in constraining the 3-loop NMHV 7-point amplitude. Mark and James Drummond and Yorgos Papathanasiou. And this sort of co-product or derivative-based approach and methods for fixing zeta values can also be applied in this 7-point case, although that's work in progress. And so we can hope to have the same kind of function level advances at the 7-point level soon that I've described here for the 6-point case. In summary, this hexagon function ansatz, when supercharged by the Steinmann conditions, gives a very effective way to determine 6 gluon amplitudes and eventually probably higher point amplitudes over the full kinematical phase space. And we need very little information from the outside, and perhaps that suggests that there will be some way to extend these results to finite coupling for generic kinematics, although there's still a long ways to go, as well as trying to better apply some of these equations to other theories, such as QCD. I should stop there. Thanks for your attention. I'm just going to leave this up during the questions, which is, I would like to advertise that we'd like to host Amplitudes 2018 at SLAC in Stanford. And there would be a school before that at UC Davis at the QMAP Center, which Yara also talked about at the end of his talk. Sorry.
Okay, any questions for Hans?
Yep.
Correctly, the problem in constructing BDS-like for multiple form.
Yeah, so what happens is that there's a what you're trying to do is find something that you can use to soak up the dual conformal anomaly. And roughly speaking, if you draw a line here to indicate a xij squared, and you want to sort of soak up the anomaly at this point, and you don't want to touch the other points, and you put one of these in the numerator and the other in the denominator, and that's why you have this dashed and solid line. And because this thing is neutral here, you can fix this, and then you can do the cyclic images to fix the other ones. But when you try to, and that similar thing works in the 7-point, except I would get lost because you have to go around a whole lot. But what you're alluding to is the fact that if you try to do it with just 2 particle invariance, you're stuck in the 8-point because this guy also goes in the wrong direction, so you can't sort of get them all working. But you could probably, I'm sure you can include 3 particle invariance, and then you could still get Steinmann constraints of the same exact type in the 4-particle case, and maybe there's just a kind of Steinmann anomaly that involves the Cusp anomalous dimension that might be related to this. So we haven't thought about the 8-point case. But there's something different that happens there, yeah.
More questions?
Actually, I have a question about the Steinmann relation. As far as I remember, it's formulated in physical kinematics, right? And you are talking about non-physical kinematics because you are working in Euclidean space.
Not always in Euclidean space. We can continue off these different sheets, and so the there are different ways to get to the physical region. For example, in the multi-regi case, we do this continuation around finite U, which you might think of as taking a cut from the Euclidean region through a 2-particle invariant. But you can also take cuts out at infinity. And that's exactly what we're sampling when we take a discontinuity. The difference between the Euclidean region and the physical region.
Okay, and,
so the first discontinuity we take out at infinity, that corresponds to crossing the first cut in and summing over those physical states. I mean, when we plot all these, all the numbers I showed you, those are all in the Euclidean region. I admit that. But in principle, you can also plot everything, including all the imaginary parts, in the generic regions. The discontinuities themselves are not Steinmann functions.
I'm just saying, because as far as I remember, it was derived under the assumption that it's physical kinematics.
Yeah, but we have physical sheets that are right next door to our Euclidean sheets, and that's what we're doing when we take this discontinuity. We're moving across a branch cut from a Euclidean region into a physical region. And then we can move around in this physical region and sort of smoothly deform it over into this one. As you can see, by moving these momenta around, you can go from this one to this one. And so you should not see a second discontinuity when you arrive at the second region.
Yeah, and so regarding the cuts, you were talking about branch cuts. So in planar amplitudes, it's also kind of well known in radio theory, old-fashioned radio theory, that should be no cuts in planar limits. In planar limit, it means planar in old-fashioned definition of planar amplitudes. So what it means, exactly what you see in.
Well, I think that's the statement that you have to cross these.
The other guys. They all cancel.
Or the way I say it is that you want to go into the multi-regi limit where legs 3 and 6 are incoming. If you try to do it where, say, 1 and 2 are incoming, you don't get an interesting.
You can see it in 6+ amplitudes if you take regi limit without the discontinuation just talked about, right?
Right.
So you can actually, if you go to the list of your constraints and to the list of your constraints, it was a statement, as far as I remember, by Amati, Fubini, and Strangolini back in 70s or 60s, and they said there should be no regi cuts in no cuts, branch cuts in planar amplitudes. So what happens? The BDS ansatz is planar. I mean, this BDS amplitude is planar amplitude, but it's planar in color, not planar kinematically, because kinematically can be non-planar.
Right.
Here you're talking both about planar in kinematics and planar in. So to the list of your constraints, you can add actually that all the cuts should be cancelled if you're talking about totally planar.
Yeah, I believe that constraint is actually contained within the collinear constraint. That branch, if I'm understanding correctly, that's a branch you can get to from the Euclidean region without taking a continuation. And otherwise, it's the same as the multi-regi corner. We kind of call that the soft limit, and it's kind of a piece of the a tail of the collinear limit, or the near collinear limit.
Okay. No question?